Uh, uh, well, good morning, everyone. So welcome to Lecture 10. Today, we're going to talk about various decoding algorithms and perhaps one of the most important things, pre-filling or key value caching. And next lecture is going to be the final practice lecture for LLMs. So next lecture, we're going to walk through PyTorch and how to browse and download models from Hugging Face and interface with it, which will get you ready to begin the project. Also, the schedule is to be determined later, but most likely about next Thursday. I'm going to invite one of the TAs to the class who's graduating with PhD this summer. And he'll be joining deep learning research team in Apple in New York. So I'm going to have him do like a mini lecture on his experience with PhD and applying to big tech companies and interview process and some general advice and Q&A. And okay, so let's get started. So first thing, decoding algorithms. So let's connect ourselves with Lecture 10 notebook, if you haven't already. So in the lecture, I guess lecture 4, we talked about 4 different decoding algorithms that's often used. So what do I mean by decoding? So assume we have trained the LLM and we're going to use it for inference, meaning we're going to do autoregressive token by token generation. Okay? So given some query, so this can be, so think about the ChatGPT case. So Q is user's query. So for example, you ask question like, how is the weather going to look like for the next 5 days? So this is given as input. So this is inputted to your LLM and converted into keys and values, queries, and attention, blah, blah, and fills all the necessary components in the attention. And given that, you're going to draw a sample. Say first one is R1, and you condition on R1, meaning you insert R1 back into the LLM as input, and conditioned on Q and R1. Now you're ready to sample the second token, which is R2. So once you sample R2, it gets inserted back as input, and it's now conditioned on top of Q and R1. And now you're ready to sample third token, etc. And you're going to repeat this process either until you sample special end of sequence token or EOS token, or until you hit the maximum decoding length. This is how the autoregressive decoding works during inference. We talked about this in the lecture, right? So if you think about, so let's say K is our maximum decoding length. And we would like to maximize the log likelihood of the most likely sequence. Okay. So we have a machine that, for example, gives us the conditional probabilities, and we like to ask, what is, so given Q, what is the most likely sequence R1 through RK that maximizes the probability? How many combinations do we have? we said length k. So size of the dictionary raised to the power of k, number of possible combinations. So we could either insert all possible combinations, measure the probability, and take the one with the highest conditional probability. But that's unfortunately very computationally expensive. It's exponential in number of tokens to decode, which is k in this case. So it's practically infeasible. So what's often done in practice is first, the simplest thing is to do greedy decoding. So each time step, you just sample one at a time and take the one with the highest logit or highest probability. Simplest thing you can do. Another thing is top K and top P sampling. So top K, as the name suggests, let's say there is, so this axis represents the dictionary, vocabulary size, and this is the probability for the first token, which is very, second token, good. And so here, to make the analogy, Q, the query was the dog is, this is inserted as input, and you're going to sample the next token, and R1, the probability of a token given the query is following. This is the probability vector. So if you do top K, let's say top K where K is 2, then you're only going to sample from these two tokens. Okay. And top P sampling, or Euclid sampling, is very similar, but as opposed to looking at a fixed number of support in the distribution, you're gonna recompute the support based on P. So you want to sum the cumulative distribution until it exceeds the preset hyperparameter P, which is in this case 0.96. So here you're gonna, if you add the first three token probabilities, these exceed 0.96. So you're going to sample from the first three tokens. Okay? Another thing that we didn't mention is you could just sample directly from this distribution. That's one of the commonly done method, and in the lecture we also talked about the beam search. So what's beam search? So first you maintain k sequence candidates at each decoding step. So here for example, k is equal to 2, so 2 number of beams. So we are maintain 2 beams. And at each decoding step, we're going to select top k next tokens for each beam or for each sequence. So here for this sequence, the dog, we're going to maintain 2 candidates based on the probability. So these have high probabilities. So the dog has, the dog and. And for this beam as well, the nice woman, the nice house, we're going to push it in as candidates for these beam. So the next step, step 3, is to select top k candidates from all the sequences. So we're going to be left with 2 beams again, and we're going to decode and continue. Does this make sense? Can you repeat the question? In step 3? So we only keep expanding from the existing beam. So this just gets ignored. So from these two beams, now you look for top K tokens. And from this one as well, you look for top K tokens. And from these K-square candidates, you're going to pick top K beam again and repeat. So the algorithm is already given to you, and you are going to implement this. So again, we have the log softmax, and why the log? In order to maintain the probability scores, it's more numerically stable to add log probabilities together. And this is the function that we're going to implement together, top K beam search. So inputs are the transformer model and the token of size 1 by sequence length. Meaning, so this is the query. Okay. And K is our beam width, or number of beams to keep. In the example, K was equal to 2. Max length is maximum length of decoding. So K is width here. Max length is length here. All right, so it's supposed to return 1 by sequence length plus decoding length, right? So this is pre-existing query, and you're gonna keep generating tokens that follow this, computed via beam search. So we're gonna initialize a list of sequences, where it's a tuple of the sequence and the log likelihood. Right? We need to maintain the log likelihood of each beam so that we can do top K searching, right? And we're going to loop max length number of times. And for each tuple in the beam, we're going to do a loop and expand K times for each beam. And of course, so PyTorch has a nice top K function that will give you top K log probabilities and top K indices if you insert log probabilities for all the dictionary elements, which we do here. And here, what you need to do is append the top K tokens to the existing beam, and also augment the log probability of the following token. Because once we have K-squared number of beams, here we can sort and select top K beams. Right? So temporarily we maintain top K-squared beams, and we're gonna pick top K beams, and then for each top K beams we're gonna expand K, top K tokens, and repeat. Right? So this is your to-do, and let's spend about 5-10 minutes here. Yeah, I think I spent about 5 minutes. So for those of you who came in late, so we have one more practice lecture left. Next lecture is going to be PyTorch and Hugging Face. And we're going to do normal lectures from next week. And the dates to be determined later, but I'm going to have one of the TAs who's graduating with PhD this summer. And he's going to he's joining the deep learning research team in Apple in New York, and I'm going to have him talk about his experience doing PhD and interview process applying to big tech companies in the US. Anyone finished? Okay, you got maybe 5 more minutes. I'm going to walk around just to see how you guys are doing. I think half of you are just connecting to Core Lab, and some of you are finished. How many of you have finished the implementation? Okay. Any questions about Beam Search? Okay, so let's look at the solution together. So here we pass the sequence to the model, get the logits, and do a softmax to convert it to log probabilities. And PyTorch's type K function will return 1 by k sized log probabilities and corresponding indices in the dictionary. And we're going to loop over k candidates and among the top k here, and get the token and the probabilities. And for the token, we're going to append it or concatenate it with the existing sequence. And the log probability, we're going to have to add to the cumulative log probability for this newly generated type K candidate. So here we temporarily hold at the end of the loop here, end of the two loops here, we're going to have k squared beams in the list. And from these k squared beams, we're going to only select type K beams. And we're going to repeat the process. Okay. So let's check the input and output shapes. So input shape is of size 1 by 10, where 1 was the batch size, 10 is the input sequence length. And after doing beam search with max decode length of 50, that means our sequence length is going to be 60 because 10 already exists and we're generating 50 tokens lengthwise. So it's going to be 1 by 60, right? Okay, so let's do decoding with our Shakespeare dataset, which is very small. And we're going to load in some pre-trained weights. And we're going to provide as input query this one, first dataset. Before we proceed any further, hear me speak. And we're going to pass it through the tokenizer and pass it as the input sequence for the top K beam search function we just implemented together. And get the output and pass it through the decoder in the tokenizer to get the actual English. So seems reasonable. By the way, the provided weights are heavily overfitted to the training set. So if you change the input so that it feels like it's not coming from the Shakespeare dataset, then I think it's going to completely break. And this was done with beam size of 2, maximum length of 50, and I guess this is about 50 tokens. So let's also look at the complexity of doing beam search. So the computational complexity of beam search, assuming a constant complexity for the forward pass, is going to be n times k squared, where n is the sequence length, and beam size is k, yk squared, because for each separate beams, we're going to expand k times, so branch factor of k. So we need to maintain in the memory k squared beams. And so if you execute the cell, how does the complexity look like? Let me actually run this. Wait. Okay. How does it look like? So x-axis here is the beam width. So it scales quadratically. So y-axis is the actual wall clock result if you execute the cell. It scales quadratically over k, which is not very scalable. And over the maximum length, also quadratically, because in attention, you're going to have to, each token is going to have to communicate with each other token, right? So you have the quadratic complexity for the sequence length. So as is, this is never going to work in practice. So what we discussed so far is very, very naive implementation that nobody uses. And what we need to learn is actually the KB caching or pre-filling. So without this, it's never going to work in practice. So what is KB caching? So without the cache, this is the version that we implemented together over the last several weeks. Let's look at the computation inside the attention. So say you have 5 query tokens. For example, this is like what is capital of Korea. Okay, 5 tokens as input. Converted to query and key, respectively. So we're doing matrix multiply, but 5 times embedding size times 5 to construct this score matrix. And then, of course, we're going to do scaling and computing softmax, and then multiplying with this value matrix, which is of size 5 times embedding size, and this attention map is of size 5 by 5. It's basically similarity among each other tokens. Right? And for the attention, it's going to be of size 5 times embedding size, and where individually we apply MLP. That's the transformer block, right? So let's say we're now decoding. So we have inserted all this information into the model, and now we're going to start generating 1 token at a time. For this new token, what is the necessary computation that needs to be done? It only needs to, so from this new token, it only needs to compute the attention with respect to the existing tokens. In order to do that, we need to have access to the key token, the key values, key matrices for token 1, 2, 3, 4. But this can be pre-computed once and never recompute again. So each time we generate, these key tokens are never going to get recomputed. We're going to just compute once and commit it to the memory. So from the perspective of this new query, it only needs to compute attention of query number 5 with respect to query number, key number 1, 2, 3, 4 in itself. So this is now of size 1 by 5. And to generate output, we need to multiply the value matrix which we can also cache the value tokens for 1, 2, 3, 4, and just compute this new value token 5. So given this, we multiply 1 by 5 attention scores with 5 times embedding, and this is going to be our attention feature where we can apply MLP to generate the next token. So it turns out during, so this is called pre-filling stage. When the query comes in, where we need to insert these query tokens inside the transformer, we can store in the memory the key matrix and the value matrix. And when we are now generating, so there are 2 stages. One is pre-filling stage, the other is decoding stage. So pre-filling is when you insert existing information. So here we inserted this sentence into the transformer so we can do conditional generation, right? So this inserting stage is called pre-filling, and this decoding stage we can now just access pre-computed key and value cache. Does this make sense? And for the mask, this newly generated token, or token number 5, can attend to all previous tokens. All right, so let me just do a quick walkthrough of KB cache class and attention class and transformer block, and you are gonna change the existing transformer class. Okay, so let's look at it one by one. So this KB cache class is new. So it's a cache that stores key and value states as a list of tensors, one for each layer or each transformer block. So the expected shape is batch size, number of heads, sequence length, head dimension. So we have these member variables: key cache, value cache, and scene tokens is how many we have pre-filled in the past. And this update method will take this new key and new value and augment it to the existing cache member variable, and also index it by the layer ID or the block index, transformer block index. Because we have these transformer blocks on top of each other, so we have these caches for each blocks separately. So for the update, very simple. So you just index by the layer ID, and you have the initial key states, value states, if the member variables are empty to begin with. Otherwise, you just do a torch.concat, and it's going to concatenate the newly computed key and value states to the key cache and value cache. Okay? Very simple. So how about the attention class? This is just copy-pasted from existing implementation that we done together in the last lectures. Of course, we have these member variables with the query key value matrix and output matrix. And the new member variable here is layer ID. And because we need to keep maintaining the layer ID, because each layer is going to have its own KB cache. So once we compute the tokens to query key value and do the positional embeddings, now the new part is we're going to now update the KB cache after we compute the positional embeddings. So this newly computed key and value, we're going to call the KB cache class and update it. And rest is exactly the same. And let's look at the transformer block. As usual, the code is copy-pasted from before. And number of heads, input dimension, the head dimension, and it instantiates the attention class, feed-forward class, RMS norm class, and layer ID. And the new part, so here that's just a normalizer. Here you're computing the attention with the normalized embeddings and positional embeddings and causal mask. Now you have additional input, which is KB cache, that you get provided as input here. So rest is exactly the same. So once you compute the attention, you do residual connection and compute the MLP, and you do residual connection again, and that's the output. So the only change is now we're maintaining the layer ID and inputting this KB cache to attention. Okay, so now this is the same transformer class that we copy-pasted from previous lectures. And you have some to-dos, not much. So again, let's just do a quick recap. So number of layers to stack, so number of transformer blocks to stack on top of each other, vocab size and dimensions, and token embeddings. And we're going to create transformer blocks n layer times and instantiate this rope embedding and RMS norm and MLP classes together. And in the call method, it's going to take as input tokens and labels, and it's going to have to return the loss and the logit, so we can do a backprop and optimize it. So just copy paste it from before. So the new part is here the scene token is going to be initialized to 0 because when we just create this class, it has not seen any queries yet. So it has seen 0 tokens so far, and now, since we are calling with tokens, we compute the embedding and position IDs. So here, that's just this is the to-do part. So we need to compute the positional embedding and apply rope and apply the causal mask. And once we compute the causal mask, we're going to call one layer at a time, where the output of a previous layer becomes input of the next layer, and do appropriate normalization, and finally apply the output matrix to convert it to map from the feature dimensions to number of vocabularies, so we can do logits and apply the cross entropy loss. So as you can probably guess here, you need to update number of scene tokens, and that's going to affect the positional embeddings, and you need to somehow maintain this cache of previously seen tokens. So when you compute attention, you can just utilize pre-computed key and values. Any questions? Is this obvious? No? Yes? So while you guys are coding, just to share with you the practical implications. So in practice, so you always have alternating pre-filling and decoding stages, right? So just think about ChatGPT. Somebody asks you a question, you need to pre-fill the user asks tokens into LLM. That's pre-filling, no decoding, right? Which can be done in one shot, right? Pre-filling can be done in one shot, right? We're not doing one by one token generation. We're just inserting the information to the matrix or to transformer. But decoding, you need to generate one token at a time. So that's autoregressive, and that's going to be super slow. So KB cache can help in terms of not having to recompute these values, but it's still going to be slow because you need to generate one token, provide it as input, generate next token. You have to do the computation one at a time, one token at a time. On the other hand, for pre-filling, you can just insert everything in one shot. And oh no. So in practice, pre-filling is not the bottleneck. Decoding is the computational bottleneck because you have to generate one token at a time, so it takes time. But so in terms of the wall clock inference time or latency, decoding is a bottleneck. But in terms of the memory size, pre-filling becomes a bottleneck because you need to hold all these into the memory, and you are bound by how much memory you can support in your machine. So this is holding a large matrix into memory, And this limits, so the implication is this limits how much you can prefill, so which then limits your context length. Right? So if you run this on, for example, on an edge device like a mobile phone, this is going to limit how much you can prefill, meaning it's only going to support input tokens of length, I don't know, a couple thousand or something like that, because of the memory limit. So you need to consider both the memory size of the underlying device and also the latency, which is majorly caused by the decoding speed. Anyone finished? More time? Okay, let's give a couple more minutes. And speaking of practical implementation, in general, you are more bound by the wall clock latency. So think your So let's think about implementation. So let's say you want to do this as fast as possible. What are the hyperparameters that we discussed in the class that you can tune in order to make this faster? So without any change of code, there are certain hyperparameters that you can tune. What's the hyperparameter that can speed up the inference time? I want to maintain the. I don't want to change the performance. I want to keep the performance. I want to do exact computation. And what is the hyperparameter that I can tune in order to gain some inference time or training time speed up? Number what? If I change number of hidden layers, it's going to change the computation. And if I decrease it, it's more likely to underfit and decrease performance. Which one? What sign? Sigma slice? We're going to generate one token at a time. Is this what you mean? So I don't want to change any code inside, and I just want to change hyperparameters. If I change head size, you mean the number of heads here? It's linked to the performance. If I decrease it, it's gonna decrease the performance. And computation is not exact. Yes. Right. So batch size is something. It's a very important hyperparameter that we can do exact computation and speed up the time, because what this does is it asks GPU to run parallel computation on batches, and this is exact computation just done in parallel. So what about batch size? How do you tune this number? Increase to infinity? Memory. Okay, let's be more specific. So you keep increasing this until fails with what? What's the output? You're gonna hit the out of memory error OOM from GPU or CPU. Right. So you're gonna increase this as much as possible to speed up the training and testing. So this is a real life story. I heard lots of so students come talk to me and say it's too slow, and it's going to take them 5 months to train this model, estimated. And common mistakes are batch size is set to 1, and KB cache is not implemented. So you're going to get like a 10,000 speed up. Right. Okay. All right. So anyone finished implementing the changes to the transformer class? Okay. So here, let's compare side by side. So previously, we compute the embeddings on the input tokens. But now we're gonna compute the embeddings on tokens that follow the cache length. Meaning we're not even gonna compute the embeddings for the previously computed tokens. And then for the positional embeddings, here we did a range of sequence length. Now we're going to do cache length. That's the starting index and ending index -1. We're not going to compute the positional embeddings for pre-computed tokens. And then we're going to apply rope, positional embedding. And here in the causal mask, the only change is here where for the mask, we're gonna just get the sub matrix starting from the cache length. Okay. Right. So let's check the input and output dimensions. So batch size of 2, input sequence length of 10, dictionary size, number of transformer blocks, input dimension, number of heads, and we're going to insert some random tokens of size sequence length, so 10 tokens, and apply transformers and initialize KB cache and do a forward pass, and we're going to end up having feature representation of exactly 10 tokens. And let's do decoding now. So here, we have pre-filled 10 tokens, or inserted 10 existing token sequences into the model. And now we're going to do decoding with, I guess, 50 tokens. Let me see how we're actually calling 10 tokens. Okay, so we inserted 10, and we're going to do beam search with 10, or K, I guess that's one beam, so not doing anything interesting. So, so here you have one more to do here. So now we have inserted and done caching of the keys and values. Now we're going to have to implement beam search with this caching in mind. So we initialize KB cache class here, and here you have to-dos. So for all the elements in the beam, you're going to do model forward, get the logits, softmax, and let's implement this to-do part together. I guess previously we didn't have this part. Okay, let's scroll back. Yeah, these are just copy-pasted from before. So let's make necessary changes to the beam search. This is going to be the last to-do of the day. Top K beam search with cache. Finished? In case it's not obvious, you initialize this KB cache, but it's not getting used anymore. Finished? Okay. So the necessary change that we needed to make when we implement decoding with beam search, or decoding in general, we need to insert this KB cache class object. into the model. So this model takes as input KB cache. So that's the only change. Make sense? So that when we have finished the beam search, we can update the KB cache, and maybe the user want to ask us another question, then it's our turn to do a second round of pre-filling and then decoding, and it repeats endlessly. Okay? All right, so you guys run the cell just to check the outputs are correct. And it's now time to check whether we had made any significant changes in terms of the computation time. So batch size of 1, sequence length of 10, which we pre-fill. And for a max length value of 10, 30, 50, 100, 200, 300, we're going to measure the execution time for decoding with and without caching. So this top K beam search, which we implemented in the beginning of the lecture, is unaware of the cache. But this new top K beam search cache with just 5-character difference knows about the cache. Right? So let's measure the time across different number of tokens to generate with beam search. Why don't you execute the cell? I think this can take some time. So in case you haven't finished this part, this is the only change. Have you guys run this cell yet? Is it running? Okay. So while it's running, it's going to look something like this. Let me zoom out a little bit. So x-axis is maximum sequence length, or number of tokens to decode. So with and without KB caching, it makes a huge difference. So red is without KB caching, and blue is with caching. So huge, huge difference. And the gap becomes larger and larger over the decoding length. Okay. Yeah, I think this is it for today's lecture. And next lecture, we'll walk through various libraries in PyTorch and spend some time actually downloading and running inference with pre-trained models from Hugging Face. And you guys will be ready. You guys are more than ready to begin the project. All right, thanks.